Hello, welcome to session number 29 in the series Microwave and Millimeter Wave Circuit. My name is Anurag Nigam, and after a long break, I'm continuing this series, and we will look into various aspects of development of a mimic, their packaging and testing. Right. So now what happens is, if you're a designer, and let's say if you are fresh out of a college, or let's say maybe 1, 2, or 3 years, or maybe you have been doing board level designs and first time you are going to IC level designs, and there are lots of things which you should know, right? So the the big thing about microwave millimeter wave circuits or mimics is going to be not the circuit design. The circuit design is well defined, right? More important is how do you package your chip, right? Now, you may have a wonderful chip, but if you cannot put it in a package and get the performance out of the package, then your chip design is useless, right? Second thing is, if you have a wonderful chip and a wonderful package, but if you cannot test it, then also your chip design is useless for me, because you cannot send it for production, right? So we will talk about testing later on. For now, we are going to focus on packaging part. Now, packages, right? Mostly the packages are quadrature face no lead packages, and I'm going to talk about okay, I'm going to talk about this particular package only, right? So there are a number of companies who do it, right? And one of them is a plastic packaging company called QP Technologies, right? So let me show you. Okay, so this was earlier called Quick Pack. Now it is called QP Technologies. Okay, so these are the commercial packages which they sell, which can be used up to 40 gigahertz, right? Now, it is not the package which basically restricts your frequency. It is the design which you do or how you package it. It's more important than the material used for packaging, right? So besides plastic, right? So in this case, the plastic is called Arlen, CLTEXT, right? So this is called Arlen, CLTEXT. This is some kind of a plastic, right? Its electrical properties are 2.94, and its loss tangent 10 delta is 0.0023. So now you see that the material, right, is not going to restrict your frequency, right? So what is going to restrict your frequency? If there are vias, but then the package here doesn't have vias, right? Or the gap between the pins, well, the gap is so large that it's not going to really hurt you. So it is not the package which is high frequency package or something. It is how you model it out, right, and how you use it. What they are trying to do is they minimize the parasitics of a package, and then they call it high frequency package. But in as such, in a package, there is nothing which restricts you on frequency, right? So now this is a plastic package. Other option, so this is the QP Technologies, right? Then there is another one. Okay, there is another one which is called Barry. Okay, and Barry does a ceramic packaging, right? So we are going to look into quick pack first, because most of the CMOS and also gas and can be packaged into plastic packages. We may go to Barry for I don't know for what reasons, but people can use Barry, which is LTCC ceramic process. But here, if you go to their products, and what I mean by QFN, this is like a open face. Okay, so this is a open molded plastic package, right? So it's an open face like this, and at the center what you see is called the pedestal. It's a ground, and then you see the pins, right? And the size of the package is usually what we use in microwave is a kind of a square. Okay, and these are the listings over here of various packages. So for example, if I want a 6 millimeter package, right, so this is the outer dimensions, right? So when I say 6 millimeter, let's see, so this is 5 millimeter, and then you go to 6 millimeter, right? So now this 6 millimeter comes in different number of pins, right? So for example, if your requirement is not many pins, right, so for most of the mimic applications, this is good enough. So when you do this, you come across this design, right? Now the thing is, you can hire somebody to do this kind of stuff, right? Or you can do it for yourself, and it's better if you can do it for yourself, right? That will cost the cost to the company, plus you will be knowing what's going on in your design. So this is the top view on the left side, and on the right side is the bottom view, and then this is the isometric view, and this is the side view with various dimensions. Now there's another point of view which I want to share. Okay, all these new generation engineers, electronics especially, they come out and say, oh sir, we didn't learn anything in 4 years, right? And whatever we learn, what is the use of all that? Now my answer to those people is the following. Okay, if you did engineering drawing properly, right, then you would be able to do this yourself, right? Similarly, in previous series, in an analog circuit, I was showing you a PLL design. If you understood feedback control system, you would have understood that. If you understand a little bit of discrete signals, okay, discrete time signals, like signals and systems, if you had done, then you would be able to do a PLL, right? If you had learned basically the devices, right, you will be able to do the circuit designs. If you had known a little bit of circuit design, right, analog circuit design, you'll be able to use that in your biasing, in your other signal conditioning. Now the thing is, most of the time when the student says we didn't learn anything in 4 years, that's your problem. You didn't learn anything in 4 years. Everything was there to be taught, and everything was there to be learned. So either the guy didn't teach you, or you didn't learn it, and now you are blaming on the system that what we learned in 4 years is useless. No, it is not. And in one case, one professor was telling me, so whatever you have learned, how much do you apply in your area? Well, everything. So when the professor has such an approach, the students will have much worse approach. So I cannot blame them, because they are mugging up the topics, and then they are producing it in the paper, but then they are not using it anywhere. That's their problem. Okay, so coming to the problem here, so if you had known engineering drawing, you will be able to transform this front view, side view, and top view, and the isometric view into a 3D design. Okay, so what all is required, right? So I'll show you a 3D design. So this one, okay, this one is this package which I have just shown you. This is exact to the dimension. Okay, so this package is exact to the dimension over here, and this is sitting on a TMM6 Rogers substrate. Now when I say TMM6 Rogers substrate, you're supposed to know something about laminates. And what do people teach in your bachelor's? FR4 substrate and PCB layout, and there should not be sharp corners, there should not be bend like this and that. That's not important. The important is if it is there, you know how to model it, right? You can swallow an elephant if you know how to digest it, right? So that's the thing which I'm saying. All those rules which they say and all that, that's not so important. If you know the physics behind, then the rules are nothing. Okay, so now what you see over here is this brown thing is DMM6. It's from Rogers, right? So let's see its characteristics. Okay, so this is Rogers substrate, and this is, says it's for high frequency applications, and this is a thermoset plastic, sorry, thermoset laminate. And what this can be used is, this can be used up to very high temperatures. That's why I have chosen that. Second thing is uh, its its loss tangent is less. That's why I have chosen it. Right. So if you see here, it says TMM3, TMM4, TMM6, 10, 10i, and 13i. I could have chosen TMM10i. I have chosen TMM6. Okay, this is because if you choose a dielectric constant close to 6, then you can make lines, you can make high impedance lines. You can also have, appropriate spacing between the lines. Now, if you use TMM10, the dielectric is 9.8. The structures are going to shrink. That means that whether your screen printing technology allows such small structures or such small gaps. So based on whether your processing, board processing allows you to do that. Another thing is people are supposed to know what is the via in a board. Now, a via, how is it made? So basically you drill a laminate and then you plate it. So that will be called a plated through, right? Or you will fill it, right? So the question is, what is the minimum size via can you do, right? Can you do a 3 mil via or 4 mil via? So when I say 3 mil or 4 mil, that is the inner radius of the plated through via, right? But the drill bit is around 11, 12 mil, right? So you understand that this is important, because if you want to pack up lots of vias close by and you do not know their process, then what is the minimum gap or pitch between vias, right? If you don't know that, you might have done the board, but the fabricator would say, oh, we can't fabricate it because my drill size is 10 mil, right? And the gap is not 10 mil, so I cannot put two vias close by. So you understand, you should know a little bit of what are the limitations of a laminate processing, right? So that's why I have chosen 6, TMM6, and its dielectric constant is 6.3, its loss tangent is 0.0023. So this is on the choice of the substrate. Second thing is, you see the standard thicknesses. If you use non-standard thicknesses, they will give you, but the problem is that it's going to cost you, right? So here, if I choose this is in mils, so this is a 15 mil. The first one is a 15 mil substrate. So the height is the 15 mil. Now, can I get 10 mil or 5 mil? Yes, I can. Now the question is, do you need it? You have to question yourself what frequency you are operating on. So if you use a very tall or high substrate and your frequencies are high, then you would have problem launching in the wave into a guided structure, right? So that's you would have modes in that which are other than the TEM modes, right? So that will basically make this lossy, right? So you, at high frequency, you're going to use a substrate which is a lesser height. Okay, so this is about the choice of the substrate. So once I have chosen the substrate, right, next there are a number of more choices to be made, right? So we will see one by one what choices. So basically what this is if I remove the lid or make it invisible, okay, so this is what it looks like. And in the drawing, let's say in the drawing, this is what it looks like. This is the top view, this is the bottom view, this is the side view, and this is the isometric view, and this is the 3D view, right? You can see the 3D view here, right? And I can remove various portions or make them invisible to help you see what this is. Now, this ground, the bottom plate of this substrate, comes through vias through this TMM6 up to the pedestal over here, right? And then there is a chip on top of it. Basically, this chip is empty right now, but I wanted to simulate the bond wires, right? So these are the bond wires. So I already have a planning in mind. So at the top, I'm going to have a PA. At the bottom, I'm going to have a LNA, right? So a PA, let's say a 3-stage PA, it's going to have a drain supply. Then it is going to have VG1, VG2, VG3, which may be controlling, which may be coming from another CMOS chip, right? Which may be controlling the gate voltages, right? And then this is the output, and this is the input. So we have a PA going from left to right, 3-stage PA, and the LNA will go from right to left, right? So it may be a 4 or 5-stage LNA. So this design I'm going to do at Ka band, right? Or let's say I'm going to do this at Q band. So I'm talking about 24 gigahertz to 29 gigahertz, and I'm talking about 37 gigahertz to 43 gigahertz. And this package basically can be used at any frequency. It doesn't really matter, right? Now, the major unknown is going to be these bond wires. Now, the question is, okay, at high frequencies, you will not be able to do a 50 ohm part. Okay, now there are two ways to do this. One is this bond wire, which is a series inductance in the load match and the source match. This can be this can be considered as a part of matching, right? That's one way of doing it. Another way of doing it is this transition itself is a 50 ohm transition. In that case, you design a part which is 50 ohm and the transition is 50 ohm. Now, how would you make a transition to be a 50 ohm, right? So that's another question. And that's a very $1,000,000 question, because most of the high frequency guys, they struggle with this. And I'm going to make it very simple for you. Okay, so let me go here. Okay, it's over here. Just 1 second. Okay, let me bring this up. I think I got disconnected. Don't worry. Okay, let me just bring this up. Okay, so meanwhile it's coming up. Let me talk more. Where were we? Okay, so we were discussing what am I going to do here. These things are, connectivity issues are always there, no matter how much technology improves. Okay, so let's consider the following. Okay, there is a ground which is continuous from the bottom plate coming up to the pedestal here. That's a continuous ground. So I will remove this guy. I'll make this invisible. So now you can see. Okay, just 1 second. Okay, it seems like there is a connectivity issue, so I'm gonna drop this. I'm gonna explain you differently. Okay, so forget about. I was thinking I have a stylus. but it's okay. So now let's open PowerPoint. Blank. Come on. Okay, so now we have a wire, and that wire is basically some form of a inductance, right? So let's say that there is a wire which is some form of a inductance. Okay, let's say this represents inductance. Okay, so this is your wire. That's equivalent to inductance. And then there are capacitances, right? So basically, so there are capacitances over here. Come on, man. Drawing makes it so easy. Okay, so there are shunt capacitances like this. Okay, so now this bond wire is an inductance, and then there are two capacitances. One capacitance is the pad capacitance on the chip, right? So basically these three paths, they have a certain capacitance to the chip, and what is in between? In between is gallium arsenide. And what's the dielectric constant of gallium arsenide? 12.9. And what is this height? This height is like 2 mil, or basically it's a 50 micron height. So that's going to result in a capacitance which is much higher than the other capacitance. The other capacitance is the board side capacitance. So basically these are these pins. Okay, they are bigger, but then the height of the board, right? The height of the board is like 381 micron. Okay, so this is 50 micron versus 381 micron. The dielectric constant of the board is 6, while the dielectric constant of the gallium arsenide is 12.9. So this capacitance on the left hand side is going to be much larger than the capacitance on the right hand side, right? Now, how am I going to make this a 50 ohm transition? Very simple. I am going to have an inductor in parallel with this, right? In parallel with this capacitor. And I'll adjust the inductor such that this results in a certain capacitance. Similarly, here I can also put an inductor in parallel with the capacitor, adjust it that this capacitor looks same as that capacitor. So basically I have tuned the two capacitors at my desired band, right? So once I have done that, right, I have a transition which is a CLC transition. All I have to do is make it equivalent to a line of a certain length, right? Usually this wire is like a, in production is like 13 mil to anywhere to up to 18 mil, or maybe it can be 10 mil to 18 mil. And this is usually, again, there are two types of bonding. One is called the wedge bonding, other is called the ball bonding, right? Now what's the difference between wedge and ball bond? Well, the difference is very simple. First of all, the major difference is the the power handling capacity, or the current capacity. The current capacity of a wedge bond, right? So the current capacity of a wedge bond. So basically, this is a wedge bond, right? So the current carrying capability of a wedge bond is like, for a 1 mil wire, is like 1 ampere for a 1 mil wire, which is like 18 mil long. So that is going to be safe, right? So if I was to do a, yeah, so in this case of a ball bond, this is going to be 1 ampere per wire. Now if it was a wedge bond, it will be like 0.6 ampere per wire, right? So now if I want the wire to carry like 3 amperes of current, okay, so if I say 6.6 amperes, so 0.6 into 4, for example, these 4 wires are there, right? So 1 2 3 4, I'm going to use this for drain biasing, right? So the 4 wires for drain biasing will allow me 2.4 amperes of current. So if I'm operating from 3 volts and I'm drawing 2.8 ampere, 2.4 amperes of current from 3 volts, so 3 volts into 2.4, so I am having 7.2 watts of power drawn from the supply. Okay, now why is it important? The important is, let's say the efficiency of a PA is 30% or 33%, right? So whatever power I'm going to get out is going to be 1/3 of that. So if I divide by 3, so I'll be able to put out 2.4 watt of power here. Okay, so now you have to be sure that for the drain you are putting 4 wires at least to get 2.4 amperes of current, right? And the others are the driver stage and the pre-driver stage. They are also combined, right? So there has to be a little bit margin on VDD, right? So you have to use 4 or 5 wires to provide the current to the chip, right? Other thing is that the gate bias, VG1, VG2, VG3, for example, the gate doesn't draw any current, so basically 1 wire is good enough. But for reliability, you should put at least 2 wires, right? Same thing is for the input, right? I'm putting 2 wires on the input, while for the output I'm putting 3 wires because of the power handling. Now most of the time a fresher, or let's say a professor or his team designs, and I have seen a number of places where I reviewed the design, they just put out 1 pad and they wanted to take out 3 watts out of 1 pad. Now that's not possible, right? 3 watts out of 1 pad is not possible, right? So that is the common mistake people do. Another thing is that if this transition on a LNA is not designed to be a lower loss or low loss, basically the loss doesn't come from the wire, or loss doesn't come from the capacitance also. The loss comes from the mismatch. So if you do not design this transition to be 50, as I told you, then you are going to see a degradation in the noise figure of the LNA, right? Or the receiver noise figure, right? So this becomes important on this side, right? So for LNA, it is the noise figure which becomes important, and for the PA, you have to deliver that much of power, right? So you have to have that many wires to take the power out. Other important aspect of this is the how do you take the heat out, right? So heat out is very important too in a PA. For example, we have just seen that if I was to deliver 2.4 watts, I am drawing 7 point something, 7.2 watts, right? 7.3 watts out of the supply, right? So where is the other 4.5 watts is going? That's dissipating as a heat, right? And in gallium arsenide, how do you take the heat out, right? So then you should know a little bit about process too, right? So for example, let's look at the manual. Okay, so this is their device, right? So look at the bottom plate. So there is a button, the backside plating, and then this is the via, right? So most of the heat will come out of these vias, right? So that's how you have to also not only worry about the inductance of the vias, but also how do you take the heat out of this chip, right? So you should have sufficient number of vias. Now once the heat goes out from the chip to the board, it has to further spread out in the board, right? So that what you have to do is, if you have more than one layer, you can thin out the entire heat using vias again, right? So let's get rid of the bond wires in the chip, right? So let's say I set them as invisible. Okay, so now I'm left with the chip, the pedestal, and the bottom part, the lead frame I have already removed, right? I have already made it invisible. Now let's see, let's make this chip also invisible. Okay, so what I'll do is I'll set this as invisible, So now what you are looking at, so I'll also make these pads invisible. Okay, and then there is another set of pads. Where are they? Set them also as invisible. Okay, so now what we are left with, this is the ground. This ground is a common, it's a ground all the way down there. So I will turn off this guy, which is your substrate. And now you can see how the ground is coming, right? So from the bottom plate, there are lots of vias which bring up the ground to the landing pattern or the pedestal of the QFN. And the pedestal of the QFN is rock solid. You see there are no vias over here. So this is just one single piece of metal here, right? So that's your pedestal. Now, why is this so important? Why the ground modeling is so important? Because at high frequency, the ground is not 0 volts across. The chip dimensions become big compared to wavelength. Okay, what do I mean by that? If your chip dimensions are let's say greater than 15 degrees or 10 or 15 degrees, then that would be considered as large and it has to be modeled, right? So that's why the ground has to be modeled, because the return currents in the ground basically decide what is their local ground voltage. So whenever your impedances are measured, they are measured with respect to the local ground. They are not measured with respect to 0 volts, because the ground is bouncing, because the ground has return currents, and these return currents are very much dependent on what is the via configuration here, right? So this basically is the entire thing is the ground. Okay, so that's what I wanted to explain you, right? So let's look at the lead frame, which is this one. Let's make this visible, and let's make the ground invisible. Okay, so I'm going to set this as invisible. Okay, so now you can see what this lead frame is, right? This lead frame is like this, and I can make this one visible. And this is your substrate. So basically these vias are going through this substrate up to the bottom pedestal. So basically you understood what this package is all about, right? So what I'm going to do is, let's make everything visible. Okay, so this is the lid. So the lid goes on the top. Another thing which you should understand is sometimes it's important at high frequencies that this should be like a Faraday cage, right? In that case, the lid, which is this lid, is plated on the inner side with the metal, right? And that is grounded at the corners. At the corners, there are stubs which go up. So for example, here at the corner, there will be stubs which will go up, and then they will be over here, there will be opening of metal here, and then this will be coated. So that is called castellation. So basically the top portion is coated, right? And the lid has the bottom which is basically metallized, and then you can solder this out, or basically there is a Faraday cage which is done for your chip, right? So these are some important things which are you should consider. Okay, so this is, I'm going to model this package for carbon, and in the other series I'm developing the transceiver chip, and that transceiver is going to give out a certain power to the PA, and also it's going to receive the LNA output here, right? So this portion, LNA and PA, is going to be gallium arsenide. So this development is in conjunction with that transceiver chip, right? So what I'm going to do here is a gallium arsenide PA, which is capable of 3 watts in 2.24 gigahertz to 28 gigahertz, and LNA in the same band will also sit in this package, right? And then on the transceiver side, there will be a transmitter receiver, plus there will be digital phase shifters and attenuators for beam forming and steering, right? So there will be 2 chip solution here, which I would do for a 3 watt output from a single patch, right? And another thing which I have in mind, so 3D becomes important, is I'm going to also study a particular because at high frequencies you have other ways of beam forming, okay, which become attractive as the frequency goes up. So this is called Luneburg lens. It's a dielectric lens. It can be used at Ka band as well as Q band or 50 gigahertz V band or even at 100 gigahertz. And what that is it is a structure which kind of looks like a ball, right? So it's a structure which looks like a ball like this. And then the focal point, there are two focal points. Okay, one focal point is on the surface. So wherever you put the source, it's going to put out a parallel beam on the output side, right? So it's kind of like this, right? Wherever you put your input, the output is going to be like columnized into one plane. Okay, so basically you can see a lot of simulations and design. So this is where you don't need so many patches, right? And then you do not need a elaborate feeding structure. This is a single structure which basically has a refractive index, or basically square root of dielectric, scaling from the center to the edge, right? And this is used in most of the stealth aircrafts, right? So this F-35 will be using it. So this one is, you can understood this is something similar to other like Rotmann lens. All right, Rotmann lens is a planar structure. This is a 3D structure, right? And this can be used for multiple beams, right? So basically you can put in one source. Every source is going to give a collimated beam outside with a very high directional gain, right? So this is what you might have to do at this frequency. I'm going to do that, and the simulation will be either in FICO or in COMSOL, right? So in Ka band also this can be used. The thing is that at low frequencies this becomes big because this has to be multiple wavelengths. So so it should be at least 20 lambda in dia. Now below 10 lambda in dia, the diffraction becomes dominant, and that's why this has to be a 20 lambda kind of thing. So at high frequencies this is attractive because this is going to be lighter and smaller. At low frequencies it's going to be large and it's going to be heavy, right? So if you want to work in your Ka band or Q band, I think this is the best way to do a directional antenna, right? A lens. So this is what is important in drawing also. Now the whole thing can be 3D printed out, right? You can use a single dielectric material with different hole performations, so to result in different effective dielectric constant. So you can scale the whole dimension from going from the center to the outwards, and that's how you can scale the effective dielectric constant. And then you can do it using a single dielectric material, or if you want to reduce the size, right, in that case, or the volume, in that case you can use different dielectric materials, but then you need a different deposition, like this is be 3D printed, right? So you need a different material to be deposited, so that will bring up the cost, right? So I'm going to try doing this with a single dielectric material. So the design is very simple, but the thing is that how do you print it out and how do you assemble this? So basically what my plan is, I will do the center sheet, right, with a different sizing of these cavities, and then I will do subsequent layers which I'll basically glue them together as a one spherical ball. So this is what I'm going to do with a 3D print, and let's see how quickly I can reach there. Well, thanks a lot. Thank you very much.